Hello there, people out in the wild, wild webs. In this little video, we're going to talk about how to find confidence intervals for population variance and population standard deviation. Okay, so I have a few sample problems we're going to look through, and here's the essential formula how you would do this. Okay, and it's going to look scary, but we'll break it down. Don't worry about it too much. Here we go. Here is your formula. It's going to be n minus 1 s squared over our chi-square value for a lower limit, okay, and that's going to be the variance that we're looking for. It's going to be somewhere in between that and this. And that's going to, let's see, s squared, and then our chi-square value for our upper limit. Okay, this does admittedly look rather scary, but let's break this down. Let's just think about what variables we need here in order to figure out where our variance, our population variance, is going to lie in between. Well, it looks like we just have a few things. We need, well, it's Christmassy, right here. We need to know what our n is. We need to know what our s squared, we'll talk about that in a second, and we need to know our chi-squared value for upper and lower. Okay? So let's think about what we have here. Okay? The n represents the number of items that we are testing in our analysis. So we're told that in this problem, right? We're told that n is equal to 29. So, boom, we have that one. Okay? I'm going to do another video at some point explaining why do we do n minus 1 and not just n itself, something called degrees of freedom. We'll talk about that later. Kind of excited thinking about it. Nevertheless, okay, so we have that. I guess the point that I'm trying to make here is don't stress these weird math problems too much. It's just you're given some stuff to plug in, and you just have to basically calculate it. You know what it is that we're given, and plug it all in, and then use a calculator. Okay, so we have n. We're testing 29 different things, so we're going to have our n minus 1. It's going to be 28. We'll get to that in a second. S squared, we're told that too. That is 24.01, so we have that. Okay, now the last bit here, and apologies for taking a little bit of time on this thing. It's kind of critical for solving these types of problems. So I'll just make sure everybody understands this. Okay, what do these chi-square things mean, and how does it relate to our confidence interval? Okay, here's the basic idea. And again, we could go for hours on this, but I'm going to try to make it as brief as possible. Think about it like this. If our confidence interval is 98%, okay, what that basically means, let's just say we have some sort of normal distribution. The data lies like this, and we have our mean in the middle. Blah, blah, I'm drawing this terribly, but hopefully everybody kind of follows this. Okay. Basically what a 98% confidence means is that we want to be sure that only 2% of the data fall outside of our prediction. Okay? I'm sure mathematicians everywhere are going to jump all over me for not being very rigorous about that definition, but that's basically what it means. Okay, well, let's just think about this. When you have data, all right, and the data fall in this little slope here, most of it is in the middle, right, and then we have less data near either end. Well, here's all you have to think about with confidence intervals. It's just, okay, if we have 98%, we want to be 98% confident, that means we have 2% of error that we are allowed. Well, but we have two tails, right? We have this upper tail here, where data get really big, and the lower tail here, where data get really small. So really all we're going to do is just we're going to evenly split the error between those two tails. So in other words, okay, look, that means we can allow 1% of error here, and 1% of error here, okay? Well, let's just think about what this means. Remember, the tail sums up on this direction to 0%, right? And the tail sums up at the upper end to 100%, right? Hopefully this is making sense. I'm not sketching this well, but try to keep this going. So that would mean when we're trying to calculate the lower and upper limits, basically, if we're allowed a 1% error at the 100% level, well, 100% minus 1%, that means it's 99% up to here, right? And then same thing goes. For 0%, we're allowed a 1% error, so that means we're allowing a 1% error on this end. Hopefully that kind of makes sense. Okay, that's really all you're looking at is whenever you're calculating whatever your upper and lower bounds are, whenever you have to use chi-square or t-distribution tables or whatever, it's just essentially thinking, okay, we're allowed 2% error, split them between both ends, so that would, in this case, be 1% each. So that means take it down from 100%, down by 1%, and take it up from 0%, up 1%. So what that tells us, and this is messy, but what that tells us is that our lower distribution is we are allowing 0.01. Think about it, that's 1% possible error on the lower end, and since we're going for 99% certainty on the upper end, we're going to go, that would be correspond to 0.99. Okay? I strongly encourage you to leave me some scathing comments for this video if this does not make sense to you, and if you'd like me to explain further or do some other examples. But yeah, just keep me posted, and I will jump in. Okay, so anyway, all right. So that means we know that given a 98% confidence interval, we know the lower end has to be 0.01 and the upper end has to be 0.99. Now, to calculate confidence intervals for population variance, we need to use the chi-square distribution. And I'm going to just pull that up. You can Google this. Here it is. Okay, chi-square distribution table. Okay, so here's what we need to do. Degrees of freedom indicate our n-1 value, and then look at the chart right here. We've got 0.99, blah 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 blah. Well, obviously we're going to be interested in that one because that's our upper bound, and this one because that's our this one because that's our lower bound. I don't know why I'm getting these weird things here. Okay, anyway, so let's just double check again what it is that we needed to find. We needed to find, okay, our n is 29, so our n-1 or degrees of freedom, it's going to be 29 minus 1, it's going to be 28, and 28 needs to match with 0.01 and 0.99. So let's look at what that would be. Let me see, let me pull this back up again. Okay, so 28 is here, this column. Let me see if I can, oh, come on. Hold on a second, let me use the mouse. See if this goes better. There we go. Okay, this is the column that we're interested in. All right, so look, 28 degrees of freedom, and we want the upper bound to be this one, 0.99, so that's 13.56. Okay, and then for the lower bound, the 0.01, we want it to be 48.28. Okay, so using those numbers, this is what we would end up with. Let me scroll down a little bit, clear up a little space. So oops, that's the second problem, but here. So using our equation, and I kind of did this a little bit ahead of time, we would have, so our n-1 value is 28, our s squared value is 24.01, and then the lower bound, hold on a second, let me just sketch this. So that means our population variance is in between these things right here, because it's the same on the the numerators for each one. Okay, and then the denominators are going to be, the lower bound was, what was it, 48.28, and then the upper bound was 13.56. And there you have it. And now it's just sort of a calculator. You just plug this in, figure out what you get, and it looks like it should be something like, check my math if I'm going haywire here, but it should be something like 13.92 and, what is it, 49.58. And that's that. There it is. So this is the population variance. It's going to be somewhere in between 13.92 on the low end and 49.58 on the high end. Okay, but the problem did say we needed to find both the population variance and the population standard deviation. Well, you remember, hopefully, what the difference is between variance, which is this thing, and standard deviation. And, oops, that's the wrong color. I won't use that one. And that is just simply standard deviation is the square root of variance. So it's just that. So basically just take the square root of everything. Gives us standard deviation is somewhere in between square root of this, square root of that. Again, use your calculator to verify this, but just plugging this in, we get 3.73 and 7.04. And there you have it. Those are the ranges. Okay? Hopefully that made sense. This video is running long. I'm going to continue with the other problems in the next video.